Hey everybody, this is video 1121 and it is the first video of our very last standard of not just this unit, but of Algebra 2. So what we're going to be talking about with this standard is we're going to be determining the solution set to systems of equations and inequalities. So we're not working with a single equation, but we're going to be working with multiple equations, looking for the common solution. So what we're going to start with is a little bit of review, but there is extension. So if the beginning seems very familiar, please make sure you watch towards the end of the video because I am going to introduce some new material that takes us from just an Algebra 1 topic to an Algebra 2 topic. Let's go ahead and get started. So the first example we have here is probably set up best for substitution. And that means that we're going to substitute 1. See, this is y that's in terms of x. Because it's y equals because it's y equals 3 plus 2x, that means it's in terms of x, that y is written as something involving x, but y is alone. So that's what this phrase is, and you'll see that a lot in higher mathematics, in terms of x. So what we're going to do is substitute this value for y into the other one, because this is what y is said to equal. So it's a simple substitution. 4x plus 5 times the quantity that we're now going to replace equals 7. And I get 4x plus 15 plus 10x equals 7. And we can combine like terms, subtract the 15 to the other side. And we're left with x equals negative 4 over 7. So what do we do next? Well, we replace this x back in so that we can find y, because we are looking for a solution to a system, which means we're often looking for an x and a y. So I substitute this back in here. It can go into either equation, but this one always seems to make more sense because it's set up to already solve for y. So there's a little bit less manipulation that needs to be done. So if I simplify this, this is going to be 21/7 minus 8/7, that's 13/7. So in the end, my final answer is negative 4/7, comma 13/7, an ordered pair solving for both x and y. Alright, our second example is set up for elimination. This is just a different method. We can go ahead and align these so that all the x's are in alignment, the y's are in alignment, equal signs and our constants are in alignment. And this allows us to eliminate one of the variables. To eliminate, I need to make sure that I have opposites. That is, that I have a 10x and a 5x. So I'm going to multiply this negative 2 across the entire equation to all three parts. And that's going to make this a positive 10x with a negative 10x as well. Please don't forget to multiply this last one. It's really common that students forget to multiply the constant. So in the next step you will add. I'm going to do 10x plus a negative 10x. It looks like subtraction, but I want you to keep in mind you are actually adding. So I have a negative 3y and a negative 14y. That's negative 17y. And this will give me 46 plus a negative 12, which is 34. When you divide by negative 17, you get negative 2. To find the x value, you need to substitute this back in, and it can go into either equation. It's whichever one makes more sense to you. Sometimes I think there's one that's more comfortable to use, but in general it doesn't really matter. So I'm going to use the top one. So I have 5x plus 7 times negative 2 equals 6. That makes 5x minus 14 equals 6. Add that over and we get 20. Divide by 5 and we get 4. So in the end, my ordered pair answer is 4 comma negative 2. Alright, this is another elimination problem. This doesn't make it Algebra 2 just because it's complicated, but it's just not pretty looking. So we are going to give this a whirl, and the first thing we're going to do is clear those fractions. And anytime I have an equation, not an expression, I must have an equal sign, and then I'm allowed to clear fractions. So you can never clear fractions unless there's an equal sign, so keep that in mind. So I'm going to clear this one by multiplying everything by 10. And then I'm going to clear the second one, denominators, by multiplying everything by 20. That makes the top equation, since I have 10 divided by 5, a 2 times x plus 6. And this 10 is going to cancel, that's just 2y minus x. And don't forget to multiply on the other side, it equals 10. For this one, it's going to be 5 times x plus 2, and it's going to be 4 times 3y plus 2, and that equals negative 60. The second step would be to combine like terms. So I'm going to distribute first and then combine like terms. When you do that, I end up with 2x plus 12 plus 2y minus x equals 10. And the second equation is 5x plus 10 plus 12y plus 8 equals negative 60. When you combine like terms, we're going to get x plus 2y equals negative 2 by subtracting the 12 to the other side. And here 5x plus 12y equals negative 78. From this point, now I can actually use elimination, and that is I can multiply one of the equations by something that's going to make an opposite. I'm going to choose to multiply by negative 5. I'm going to change my pen because at this point I've written quite a bit. So I'm going to multiply everything by negative 5. That makes negative 5x minus 10y equals 10. And here I have 5x plus 12y equals negative 78. That one remains unchanged. So the 5x's cancel, and because I'm adding these together, I get 2y equals negative 68. So y will equal negative 34. Remember, it doesn't matter where you substitute it, but I really don't think that substituting it up in the very beginning is going to make a lot of sense. So I'm going to pick one of these two down here to substitute into, and in my opinion, the first one seems a little bit simpler. So I have x plus 2 times negative 34 to equal negative 2. That is x minus 68 equals negative 2, or x equals 66. So 66 comma negative 34 would be the final answer for this elimination problem. Alright, so these are the two of the three methods that you learned in Algebra 1 when solving systems. The third method was to graph two lines and see where they intersected, or if they intersected at all. In this case, I didn't share that with you, although we definitely can take a look at those problems together in class. But just remember that this is really solving the same thing. I am looking for where these two equations share an x and a y, and typically we find x's and y's when we're graphing. So it is the same as looking for the shared intersection of these two equations. Alright, here we go on to the Algebra 2. So I'm going to introduce some new vocabulary to you. And the new vocabulary begins with the word consistent. And when we talk about consistent, we're talking about a system. And a system is consistent when there is exactly one solution. And of course, that's the most common case. Most common case is that these two lines are going to intersect and we're going to have a single solution. So that is the most common case. Then we have another case called inconsistent. And the inconsistent one is when we actually have two parallel lines. Okay? So this is taking a look at when we have two parallel lines and there is no solution. So a system is inconsistent when there is no solution, and that's typically because they're parallel lines. Okay, so there's no intersection, so these are inconsistent. Okay, it's not going to give us a solution. Now the second words actually describe the equations within the system. They do not describe the system itself. See, the first two words are saying, well, the system's going to work or the system is not going to work. Okay, and the independent means that the equations are independent of each other, and this goes right along with being inconsistent. So inconsistent and independent go together. So we would say that the equations of a system are independent. And that is that they have nothing in common. So they lead to no solution just the same. They never share at any points. All right, and then we have dependent. And dependent is if we have infinitely many solutions. So this is equations, this should be plural, equations of a system are dependent if they share all points. That is, that they are the same line. So a dependent system is when two lines are exactly on top of each other. So no matter what, they're sharing every point that's on one line is also on the other. They are dependent on each other. All right, so this is just a little bit of vocabulary, and we're going to go ahead and use some of that now. Okay, in our first system here, and we're going to do this one and one more, we're going to solve it and we're going to state whether it is inconsistent or if it has infinitely many solutions, meaning are the equations dependent? Okay, so this is if the system is inconsistent, and this is asking are the equations dependent on another. If they happen to be dependent, meaning having infinitely many solutions, we need to write the solution set with y arbitrary, and I'll explain what that means if that happens to be this case. So I look at this system and I think, well, my x's and my y's are all aligned, so I'm going to use elimination. So I'm going to multiply the first equation by a -3. That would make my x's opposite. But it also happens to make my y's opposite, and it happens to make my constant opposite. That means that since everything canceled, I have 0 equals 0. And what this means is that I have dependent equations or infinitely many solutions. I want to explain that infinitely many is not the same as all real. See, all reals would mean that you'd shade in your entire coordinate plane, that every single combination of ordered pairs would matter and make sense in this equation. However, that's not true. Infinitely many, because there's infinitely many points on a single line. And because this is two lines that are on top of each other, really representing one single line, there are infinitely many solutions to it because there are infinitely many points. However, it's not all real solutions because that would cover the entire coordinate plane. It'd be more like a blanket instead of a line. So it is not the same thing, and we will use the correct language. We have infinitely many solutions. So this had a condition. It said if there were infinitely many solutions, we need to write the solution set with y arbitrary. So this is how we will do that. When we want to write it with y arbitrary, that means I need something that represents x and I need y. So how can I write something that represents x? Well, I can find out what does x equal. In other words, I need x in terms of y. So I need to write this as x equals. Pick either equation, it's not going to matter given that they are the same equation. So I'm going to pick 3x plus 5y equals -2. And I'm going to solve for x because I want x equal. So 3x equals -5y minus 2, and x equals -5y minus 2 all divided by 3. You see, this is going to be my solution. I have -5x minus 2 divided by 3, comma y. this is my ordered pair. I wrote a y, an x in there. That should be a y. They should both be y's. That's my ordered pair. You're thinking, how does that make any sense? Well, remember that if I choose a y value, then I'm going to get both my x and my y out of this. For example, if I choose y equals 2, okay, then I substitute in 2 into the other position. That's negative 5 times 2 is negative 10, minus 2 more is negative 12, divided by 3 is negative 4. So I get one of the ordered pairs that happens to be on both of these lines because the lines are the same. I can choose another value for y. Let's suppose I choose 1. So I choose a 1 for y. I put a 1 and then I get negative 5 minus, or negative 5 times a 1 is going to be negative 5, minus 2 is negative 7, divided by 3. It's negative 7/3. So no matter what I do, I choose a y value and I can find another value that's on the equation, on the line. So this was what we wanted to write, and we can definitely practice more of these together. Let's do one more example. All right. For this one, the same directions if it's inconsistent or if it has infinitely many solutions. Once again, my x's and my y's are all lined up, so I'm going to go ahead and multiply the top one by negative 2. That gives me negative 6x minus 4y equals negative 10. I notice that both my x's and my y's cancel, leaving 0 on the left-hand side, but I get a negative 2. This is a false statement. That means that I wasn't able to eliminate one of the variables to solve the other because they both eliminated, but the lines never intersected. So that means that these are inconsistent, as if there's no solution. So I would say the system is inconsistent. There are no solutions. Okay, so I'm asking someone to say to me in class tomorrow, do I have to write all that? And then I want you to guess my answer. All right, well, this was our last problem. Great job. I hope you see that there was a little bit of an extension in Algebra 2, and we are going to continue that together in class and throughout the rest of this standard. Great job.